Hello, gentle readers. Logos 2000, 21st Century Foundations. Today from a study with Ross Finlayson, September 26th, 2025. About 2:45 in the afternoon. Today in Logos 2000 will be just sort of a continuation of the previous episode about the inverse spirals, which is involving going through a box of books, sort of a grab bag assortment of books, and from it establishing just some context, some filler, a bit of a lull, yet not quite a pause, of what is really a sort of a way to help incorporate what would be opportunity of influence and inspiration from what may be these sorts, references in the field of science or mathematics or logic or physics or philosophy that go toward making it that it helps to establish a brief distancing from otherwise this wider context, and then for the focus then to so follow as trying to just kind of complete this idea of the discorso logos and the Logos 2000 for this 20th Century Foundations bit, that it's also just kind of getting through the rest of this box of books. So before I start with that, then a few items I thought to mention were kind of about physics. So in physics, one of the ideas is that we have premier theories of physics, and they're fundamental theories of physics, fundamental physics, and that they're theoretical physics, and then that's with regards to explaining all the fields in the applied and the practical theories of physics, and as with regards to the experimental physics. So over the past 3 decades or so, or about 4 decades, there have been several main experiments of big science, where big science is science that can only kind of be really afforded by large bodies, usually governments, for example, the United States, and as part of its primary science and big science. So when it comes to the sky survey and the space observatories, that's largely the realm of big science and mostly courtesy United States investment in research and development. And in the macroeconomic sense, you can look back over at least 100 years and see that for example, the United States, and applies to most other countries in the world, their growth in productivity and thus GDP, and avoid the Malthusian dilemma and all that, is directly correlated with the macroeconomic expenditure of research and development. And so sometimes it's hard to see kind of the benefits initially of tier 1 research, say, and these kinds of things. But besides the fact that it's the reason so many tech transfer seeded companies have been able to commercialize these sorts of developments courtesy the research and development infrastructure on the large scale, that it's more than meets the eye in its investment, and tellingly, it's kind of the only indicator of growth in the gross domestic product. So that just being inspired by mentioning big science, it's as well necessary to have it. It's like, well, we can't have any boondoggles in big science, where a boondoggle is kind of like something that's just no good. It's gone wrong. A folly, say, where a folly means something where somebody throws a lot of money at, yet is not of the lasting value of a sorts. So in the big science, with regards to the premier theories, one of the things about that is that the premier theories are very much solid and bedrock, and meaning fundamental for all the other theories to build upon. And then as you follow these sorts of discussions, and that's it's not always the case that those represent exactly that they're either A, truly fundamental, or B, not having attached inaccurate or inappropriate baggage the theories. And so there's lots of examples of that in these sorts of talks here. And so with regards to the 3 or 4 decades ago in the Sky Survey, what's sort of been arrived at is that for the decades and decades before that, one of the key features discovered about the cosmos with regards to things like standard candles and the hydrogen line and interstellar dust, theories of stellar formation and pulsation, models of the ephemeris and the geodesy, and as that may be, an orbifold of all the things, is that the universe appeared to be falling away or expanding. And so after the idea of the Big Bang Theory, which is that, well, things, if they're neither created nor destroyed, at some point they were either created or it's eternal. And the idea with the Big Bang Theory was a very simple one, and in accordance with other stories of origin that start from nothing, that say that there was nothing and then, or we don't know, and then out of it sprang the universe altogether, or as a well-formed thing. So the idea is that according to basically the constitution of stars, their elements, according to models of the stellar furnace, of the transmutation of elements, and the sky survey, that it's possible to arrive at, with that, and then given that the universe is expanding at such and such given rate, to extrapolate backwards to when that would be, and then according to the contents of the luminous matter surveyed across the entire observable universe, to arrive at numbers like, oh, the universe was born 13.6 billion years ago, and in this inflationary epoch it arrived at somehow making for chirality, or the distribution of matter versus antimatter, and the balance of electricity versus charge, and all these different things with regards to the inflationary epoch, and then the expansionary cosmology. Why is it just all falling away and growing? So that was very well borne out by the data. And it also fit with these premier theories of the day, including relativity, the Einstein's theory of relativity, with regards to some, or at least one of the possibly considered predicted or theorized aspects of the geodesy, and showing that the length contraction and time dilation both were kind of happening, and then also that it met up with reasons why the Big Bang model after Lemaitre and Eddington and the kind of the experiment that was said to give the entire credence to relativity theory, according to the Sky Survey, came into being. Well, 30 or 40 years ago, then there were experiments put online to help identify basically the anisotropy and isotropy of the universe, because if space-time is so curved, and there's a cosmological constant in the gravitational field equations to make this kind of like it's bending vis-a-vis that somehow it's not bending, or that it curves back together. The anisotropy was like the wide microwave background anisotropy explorer, WMAP, and the cosmic microwave background radiation was to be surveyed. And so when this came back, then it said, well, the universe is flat. So this was among other experiments already kind of chiming in and building according to the measures of the inference, and like, well, according to this theory, what would it so be that it can arrive at like so, and what's our statistical confidence like so? That the standard deviations making a significant result that the premier theory is... and you can just say it's Newtonian if Einstein's gravity is just Newtonian in the limit, that the premier theory was falsified. So this is called two things today. It's called dark matter, because galaxies spin but they don't fall apart, and dark energy, because the universe appears to be flying apart. So over the years, and before the James Webb Space Telescope has really made the Hubble tension a bit too tense, is that the two mass discovered that the redshift was only about 0 when it was of the 100% was presented to be, that the redshift and blue shift, this complementary quantity that according to Doppler effect generally we can say that something's receding or approaching, that since the WMAP and the cosmic microwave background and two mass, and then the James Webb Space Telescope, that the theory is establishing certainly that dark matter, meaning something is missing from Einsteinian or Newtonian theory of gravity, and dark energy, meaning something is missing from a Lemaitre or inflationary theory or an expanding universe theory of the universe. Those have been disproven, say. It's no longer scientific to say kind of rationally, since it's 6 or 7 standard deviations, 6 sigmas or 7 sigmas out from those being possible, to say they still apply. Now, while this is so, you'll often see stuff come up in science in the articles in the news and be like, verified again. The theory is still verified again, because of course new physics is always what one of the main things to find is, because it offers entirely new milieu and realm to be explored and exploited in advantage, such that thinking beings can use their intelligence to make the world a better place, say. Better living through science in this sense. Where better living through chemistry was an old slogan of the chemistry industry, which on the one hand has provided so much that makes daily life possible, and at the same time is responsible for some of the worst environmental catastrophes and these kinds of things. But better living through science vis-a-vis new science. So what I wanted to mention was that this. So here the idea is that the premier theories are general relativity, which is basically a theory of motion in space and time of objects, and then the relative part is that there's no absolute motion. And so motion is just in the theory mathematically, motion is modeled as from 2 different observers, that it's not necessarily in the same scale as of the speeds and this kinds of thing. But there is, for example, an absolute space and these kinds of things. So one thing to kind of point out, that a recent article or a kind of series of ideas was like, well, space-time doesn't exist anymore, and that's I'm kind of incredulous at this, because it's like, well, say what? And there's like, well, just like when space-time came around, and so now time is a free parameter. Now some of the theories just want to say space-time doesn't even exist, and it's just all events. And so, in fact, it doesn't even matter all of the connectedness and the intelligency of reality. It's just this individual type thing. Well, this strikes me as a totally sort of not just non-scientific, but kind of antithetical to reason kind of thing. And also, it's kind of just like it's wrong. And when I say wrong, it could be one of 2 things. The one is just incorrect. It's not correct. It's wrong. And the other one is bad. It's wrong, and it's not right. And it's not just a matter of saying in a positivist theory that it's like, well, in our positivist theory, we're just going to have a space-time, and it's in our theory, and so we can just model things according to it, and if it lines up, it's okay. This is instead some idea of saying, well, space-time doesn't exist. It's all just events or something like that. It's like you've left all this other realm of the apparatus behind, and then to say that that's a positivist theory, and so it can't be wrong. That it's invincible. It's like, I'm invincible, invincibly ignorant. To have that be so is just considered, it'll wash away, much like a bunch of these other recent sorts of putative theories of the wobbly sort, well, that was a couple years ago, or some of these other various things is like, well, I've solved it by applying a power law, and I found a log linear relation, and that must be the new theory of physics. And it's kind of like, well, actually, you can just do that to your daily walk and find that it's not much changed, and you're still adding up to the same kinds of things. That's just one of these examples I want to point out that's considered just absurd. This is one of those things. And here, furthermore, it's kind of rolled back to be like a space and time, with just 3 dimensions of space, an array of time. So more of like 3.5 dimensions. So time is never negative. Time never goes backwards. And that space contraction makes for time dilation and length contraction together. So it's not ever a problem of having what one might say breaking not just the intuitions, but the connectedness and the continuity of these things otherwise. So Einstein's relativity then is just no absolute motion. Then the special or restricted relativity part usually has attached also that light speed is a constant. Light speed is a constant. And there's various ways to consider how it is so that it's a constant of the rate of change or motion of the image so carried and the intensity or the image of light, the quantity. So then the other side is quantum mechanics, and it's after a statistical interpretation, and it builds after electron physics, largely a model of atomic physics, and then mostly about electrical current and the largely Ohm and Kirchhoff being supported by that. So largely that the Newtonian is supported by Einsteinian physics, and largely that the classical electromechanics are supported by quantum mechanics, say. Besides just the stoichiometric and chemistry and bonds and all that kind of thing, which are so great and are kind of more from around since the old quantum mechanics. So relativity theory is just a perspective on motion, and also light speed is constant. And then there's a cosmological constant, and it was discovered that that's not really any finite positive number. The universe is flat since the last few decades ago, but it's not zero either, because something's to move at all. It's a mathematical infinitesimal is the real idea. And then similarly, the mass to charge ratio kind of also goes to zero. This gets into the running constants on either side of these two premier theories, so that Einstein's relativity is space contraction again with space frames and frame spaces. And then the quantum mechanics is continuum mechanics underneath it. So you can call that superstring theory if you want. You can call that, you can look at any of the number of theories like quantum chromodynamics or a Technicolour, quarks all the way down, turtles all the way down, quarks all the way down to infinity. Superstring theory, that is continuum mechanics. And then where's gravity supposed to live? Isn't gravity the only law that actually is supposed to be? Like, what goes up must come down in the terrestrial frame, and that everything else is just kind of like it's just kind of matters of motion, rest. Then with regards to gravity, how that can be is it's called the fall gravity, or here it is considered so, for that to be a premier theory. And otherwise, both in relativity and quantum mechanics, you can show that it violates the conservation of energy, which would break all the theory. So to be a fall gravity, it's just like, well, from the farthest, faintest outside of the universe, we're all just naturally falling together. And so something like the earth, the ground beneath our feet, simply blocks us from the rest of the universe, and so that we naturally gravitate towards it, this constant sort rate. And so the premier theories are thusly. Then trying to figure out, it's like, well, dark matter says that the galaxy would spin apart and fly apart because there's not enough luminous matter in it to hold it together. But if it's just on a spinning disk, we kind of put zero-eth laws of Newton underneath for Einstein to sit on. That then he could say, oh, well, now thanks you figured out my linear stuff, you've kept it an inertial system, and then for making it a differential system, as long as it's an integral and differential system, all I care is that it's Lagrangian. A differential and integral system parameterized by time. And as with regards to harmonic functions and the Laplacians, the potential theory, that it's the sum of history, sum of potentials, that the idea then these zero-eth laws of motion make for us like, well, it's just a spinning disk. We're just as outside it as it is inside its own disk. And so dark matter is explained by this zero-eth laws of motion. And then for dark energy, it's like, well, what's this? If all we saw before was redshift, and then all we get now is half and half, redshift and blue shift, then what happened to this? And so the idea is that, well, light has got a constant speed, say. And then one of these other concepts that changes over time, like the ether or the oh, what was that other one? But the ether or the supplementary and hidden variables of quantum mechanics say. So the ether on the one hand expressing all this Machian that was supposed to be part of Einstein's total field theory, and then the supplementary and hidden variables on the other hand representing in quantum mechanics was supposed to be all this continuous background and these super classical, the super elastic say, which is a new word I just made up. That then for this gravity in the middle, and then figuring out for mechanics that, well, we can explain dark matter and rehabilitate otherwise a theory which would be broken. For the mechanics, that here it's considered out as part of motion, moment in motion, the world's turn bit. And then for the light, then getting back to the light, as was mentioned, the ether is the idea that the Earth is spinning in an orbit about the sun, much as we are about it. We're not actually so much resting on the Earth as falling together in an orbit that we have a terminal or ended orbit on the Earth. But anybody who actually leapt far enough into space could make orbit again. It's all orbits and not the geodesy where we're just on our world lines, which is just another way to do it, to model it mathematically when I say do it. So the idea is then the light is a constant, and then as according to it enters the rotational frames, it has an effect that furthermore it kind of rolls over the focus. And so this is related to some theories of Fresnel. I'll say Fresnel instead of Fresnel, or the correct pronunciation in French of his French name, Fresnel or Fresnel. That Fresnel is accorded sort of this idea that light speed is a constant because it has to do with our ether drift and stuff like this. And that Lense-Thirring and frame dragging experiments also in the past few decades have made it so that about at the right distance, and same with the Eotvos experiment, it's kind of like, turn it in the right direction, because then what it arrives at for these notions of the ether hypothesis, so the existence of an absolute space, say, the space does exist. And Einstein, you can find in him on Sidelights and Relativity, he says, yes, ether does exist according to Einstein. That, and for example, per the previous comments, against this new theory just says, well, just it doesn't exist. Was that a total field theory? No, it's like, oh no, this is just, we just want to be able to pick them and put them down, the smallest little theories, and say it's true. And anyways, that's almost is received as much rejection here as material implication, but not quite, because that's just a failing, the idea of having a broken theory, but break-in theory is considered an offense, say, an insult. So anyways, how do we rehabilitate the premier theories of today, which besides pointing at each other 120 degrees order of magnitude away from each other, because general relativity and quantum mechanics don't agree. So we can fix that with fall gravity in the middle. And then we'll what about dark matter and dark energy, invalidating Newtonian theory or Einsteinian theory of gravity. It's you just kind of fix up mechanics a little bit underneath, and that's repaired. And then for light, then carrying back into this discussion about how the light arrives in the picture, is that light just kind of makes all the circuits. Kind of like we think about the wave as making all paths, then the light goes all the way around the focus. And so we can look at how did this light get here, and then why did it seem to take so long if it's always just seems so fallen away when in other spectra, or according to other experiment, we remove this redshift bias. Or as you can find it in the literature today, it's called redshift space distortion, which is then having all these different ways kind of pecking and poking holes in it, not quite coherent together. That it can make it so that in the ether, as the Earth revolves around the sun and the sun revolves around the spiral arm, and basically in our observable universe, that the Earth is going about half light speed as we measure it today. And everywhere in the entire terrestrial setting, because all the light that's ever been measured is coming from the outside universe, is arriving on Earth, is according to Earth's position, and that and the entire cosmic clockworks, the cosmic bellows of all the influx and the stellar pulsation of stars, the cosmic clockworks of all the gravity, the geodesy here in orbifold and trajectifold, on this continuous manifold according to this gravity, a fall gravity in the middle. It's the only way that the theory doesn't just break itself. That thusly we can arrive at a way that's like, okay, we still have all the mechanics by just fixing it a bit underneath, and relativity and space contraction are still things, and also light is the L principle is still a thing, and then also for quantum mechanics, it's like, well, we got to figure out continuum mechanics, and that's got its own thing that's going on, because mass and length and time kind of result being kind of degenerate at the length scales or the mass scales or the time scales of the Planckian. That then with having a fall gravity in the middle instead of like a Newtonian pull gravity or an Einstein kind of follow gravity, it's just and not really kind of Lesage and Fatio's push gravity, it's just kind of a fall gravity. And then it's kind of more oriented towards the shadow cone instead of the light cone, gravity's cone. This way, this sort of putative theory sort of doesn't have all these problems that all these things have, and not that dark energy or dark matter are problems themselves problematic, although we must consider as human creatures and our relations among peoples of different polarities and these kinds of things, that we frame that to be the positive thing about dark matter and dark energy is it's basically it's being missing showed us that the theory needed something to explain what it is, and so that it is again the same matter and it is again the same energy, and there's nothing missing from it. So in that manner, it's considered here that that's the way of things, and it will always be so. And pretty much anything that doesn't really explain that has got at least 120 orders of magnitude difference from all of big science's big data. So that would be wrong. I believe that's accurate. All right, then, let's get into these books, say. That took 27 minutes or so to spout out. It took a bit longer than that to figure out. Let's see what's in the box. Molecular structure, the physical approach. Oh, this is Brandon Speakman. So atomic theory is that it's all atoms and only the bonds between them, and it's only atoms, the stoichiometric, that is chemistry, the end. And so molecular structure is like, we get resonances. As soon as you put two atoms together, they make a molecule. And so the structure above that, we can't really keep talking about it just as if it's all atomic, because the species of the isomers and the polymers and all this has to do with the molecular structure and the molecular chemistry. Hydrophilicity, how does water behave? The universal solvent. Things to do with, for example, like how does metal conduct, or any kind of things to do with the aggregates. Now, quantum mechanics already has a picture. It's like, well, everything's a particle and a wave, even molecules, even macro scale objects kind of have a frequency and a wavelength, besides being bodies and extended bodies. So this molecular structure, though, Brandon Speakman goes to helping to explain and explore, and this was like almost 80 years ago already, at least. See, it says it was 30 shillings net. This book gives a general account of the application of physical methods to the analysis of molecular structure for in an undergrad. It concentrates on principles rather than practice, explaining in greater detail those passages which need a very clear understanding of the nature of the molecule. So, this book then was published in London by Edward Arnold Publishers Ltd., by Brandon Speakman at the University of Glasgow, or Glasgow in 1960. And so this goes well with one of these other books over here that's called about the molecular physics, and a couple of other ones. But this would have been very relevant to all went into anything that was kind of like the nuclear theory of nucleons, which is all about isotopes and nucleons, and this being all about molecules, and then and so that was Sachs, and this is Brandon Speakman. That then this gets into nuclear resonance spectra, the vibration of molecules, polarizability, and the Raman effect. So the Raman effect and Raman scattering, it has to do with molecules above atoms, say. Structures and diffraction. Then this gets into where molecular chemistry is just called structural chemistry, vis-a-vis atomic chemistry. So you know your inorganic and organic chemistry, that inorganic basically doesn't involve carbon in the double bond, and then you know about bonds like ionic bonds and covalent bonds and double bonds and these kinds of things, and then and you know about like isomers and monomers and then polymers and these kinds of things from your chemistry classes, so or your own discoveries. So this is about the difference between atomic chemistry and molecular chemistry, that they are one and the same, yet two different things, about molecules and atomicules. So I don't know any other book of that era that kind of covers the subjects in quite that way. But there's a more modern one here. I don't know if it's sitting right here, but there's something about this molecular physics. Okay, now these books go together. This is just kind of a series, and what it is over on the shelf. I have something that's like Gordon or Roger Friedman's digital telephony, and so what that is about is digital telephony, and up to like signaling system 7, or the modern way that calls are routed, and then now that's that's like for international calls and stuff like that. Whereas today as well, everything's so much on the network that it's an Ethernet network so much, and with the various protocols like ATM and that being a networking protocol on the backbone of the networking, and these kinds of things with regards to things like border gateway protocol and IP routing, internet protocol, and all this kind of stuff, ubiquitous everywhere. And then comparing that with something like the packet core and all the wireless modems in the world, or phones, they're all kind of one thing when you start to look at it. And then that there's digital telephony from the 90s, a really great book, and then that telecommunications standards, which is a really great book and thick book. So this book is Abbott on telephony. So this is the phone company with like 2 copper wires, a battery to drive the significant amperage from the switching board to ring the bell, and then, which is a high voltage and high amperage, and then the actual communication is quite a bit lower one, because ringing the bell was like, it cost the most of all the system just to ring the bell, and then after that, when it was connected, then it was a little bit easier to amplify that, say. So anyways, these books cover, this is the locations of central offices, switchboards in the central office, the substation, aerial lines, the cable plant. Not so much relevant these days. Yet, if you wanted to implement a telephone network, it would be kind of along those lines. Let's see. Mathematics for the general reader. This is Titchmarsh. So Titchmarsh is famous for a couple of different things, and I'm not quite sure what they are, but it has to do with linear algebra, if I'm not too mistaken, and some things to do with complex analysis. This is a textbook, and then let's see what he kind of has as focus. Since 1931, he's been a Savilian professor of geometry at Oxford University and a fellow of the New College. Served from 1945 to 47 as president of the London Mathematics Society. It reminds me of this one guy who is the president of the American Mathematical Society. So his name was Huntington. And so Huntington, when it comes to logic, has got the Huntington postulates. And so just like, we can look at Chrysippus and say, hey, we need not be fooled by irrelevant, non-modal, quasi-modal accounts. Like someone saying space-time doesn't exist could then use to make any such absurd statement as they cared to make so, and say it was so. We don't have to listen to that. Even if our ears can detect it, it can detect its incongruity with reality, say. So Huntington's postulates are kind of like Chrysippus's moods in that sense, because they give for universals and particulars a way for logic. So instead of saying, oh, well, that just give like a Russellian retrothesis requirement or something like that, is Huntington says there's ways to figure it out. So as the leader of that entire society, it wasn't just because, you know, he was the gland-handing, you know, smooth-talking sort of politessing, finessing, those being the only positive words I can think of for politicians that aren't just like great statesmen and leaders, you know. Talking head. That instead, this is showing that the leaders of these societies were mostly there for a reason, for their great contributions to science and mathematics. So he introduces quite a survey of mathematics: counting, arithmetic, algebra, fractions, the use of numbers in geometry, irrational numbers, indices and logarithms, infinite series, pi and e, the square root of -1, trigonometry, functions, differential calculus, integral calculus, and aftermath. All in one little book here. So if we turn to the aftermath, he said Bertrand Russell said that mathematics is a science in which we do not know what we're talking about. We do not care whether to say it's true. So in this sense, that we could say this is an account of logicist positivism, and there wouldn't necessarily be much in this that wasn't particularly old hat. The Anchor books have many other books in them. I don't really see anything that sticks out directly as relevant. But Titchmarsh does have some actual developments that are of relevance. Electron physics, the U.S. Department of Commerce, National Bureau of Standards, Circular 527. So this is electron physics, it says, and here the best considered reference is O.W. Richardson's, Owen Willen Richardson's electron physics, an electron theory of matter. And then there's Jackson, I guess, is kind of the biggest, considered the most usual textbook in the entire field of it. But then this is something different. And what it is Proceedings of the NBS Semicentennial Symposium on Electron Physics, held at the NBS on November 57, 1951, the National Bureau of Standards. So before there was the National Institute of Standards and Technology, or Science and Technology, and this was the National Bureau of Standards. So we have our standards. And so this is National Bureau of Standards Circular 527, issued March 17th, 1954. So talking about the big science and the government's R&D that made it possible for the growth in the GDP to make a functioning free market economy, this is an example of one of its outputs. A.V. Aston, Director, NBS, National Bureau of Standards. The year 1951 marked the 50th anniversary of the establishment of the National Bureau of Standards. As part of the scientific program of the National Bureau of Standards for this year, 12 symposia were organized on scientific and technical topics of considerable interest. The Symposium on Electron Physics was the 10th of the series and was organized under the general chairmanship of Dr. L. Marton of the NBS Electron Physics Laboratory. Electron physics, for the purpose of the symposium, was interpreted to mean the physics of the free electron in distinction of physical electronics, which is study of the bound electron. For many years, work has been conducted at the National Bureau of Standards on the different phases of the physics of the free electron, but recent years have seen a more organized effort towards some of the objectives of research in this branch of physics. This symposium was arranged around two such topics in which NBS activities have been carried out, i.e. electron scattering and electron optics. These topics have been the subject of some earlier research conferences, but it is believed that this is the first time the symposium is devoted in its entirety to these subjects. So this helps to go to show that when you look at something like O.W. Richardson, he's like, hey, there are at least three ways to look at electrons. In fact, also I've introduced definitely two constants called c that are just right above and below light speed. And whereas light speeds is a constant, then these kind of vary, and where it's supposed to be frequency and wavelength, that according to light having that as being a constant, for electromagnetic radiation means wave velocity, according so that the frequency is kind of like the wave velocity, and the wavelength is according to the wave velocity of electrons in those. And then for the static current and electrodynamics, electrostatics, and then here are the free and bound electrons. These different ways of looking at this are tetrad of quantities, a tetrad of forces, a tetrad of fields. Not really a tetrad of elements, say, that's being the old-fashioned earth, air, fire, water, but neutron, electron, proton, neutron representing mass, charge, light speed, and nucleon lifetime, say, for a tetrad. That in that, then thus so electrons have at least 3 degrees of things that they fall out when matters of pressure, representing things in a fluid model or a gaseous model as of pressure and vacuum, and that it helps to show that they're particular empirical fields. And so electron theory itself isn't just one thing. And then that it's used throughout with that, equating that to a photon and then relating that to a neutron and then calling that, according to magnetic strength, all one theory, the electron theory of matter. Here's that there's kind of a tetrad of theories. There's electron theory, muon theory, hadron theory, and neutrino theory. So any one of those could kind of be like the particle. That here it's about electron physics. Diffusion of electrons in infinite media. Scattering of electrons by nuclei. Scattering of electrons. So you got Seliger, Botha, Blanchard, Feshbach, Engel, Scott, Ming-Cheng Wang, Eugene Guth, Gerhard Grutzinger, SGLS, J. Carl, W. Glaser, Busch, Bremer, on a phase contrast theory of electron optical image formation, phase contrast. Now that introduces a new angle. Theoretical study of quality of images by A. Marshall. Now that might be actually interesting. Lentille electronic by P. Grivet. Property of the paraxial ray equation and some consequences by P. A. Clavier. In our light theory here, we kind of have a parallax. So this is for perspective and projection, and it's all built into all the usual idea of the observer and all that kind of stuff in relativity theory. And the peripheral parallax, which is kind of like that when something enters the peripheral vision, it's kind of established its own sort of parallax, even though there's not two sides of it. This kinds of things. Kind of like geometry has one where it's like, well, there's a super-Euclidean geometry where parallel lines meet at infinity. And there's another one where, like, at 0, it's that straight lines bend. What? Is that even a geometry anymore? Well, it's super Euclidean, but some people will have that doesn't exist, right? That's one of the things though that I invented that or discovered that as an idea. It was for myself at least. Well, I've heard of super Euclidean geometry where the parallel postulate is let out, and this is just the one where it's like that a straight line is two angles opposite each other. It makes a way to have geometry if you need to kind of fold it up in a box, say. So a theoretical study of quality of images by A. Marshall. Grivet, elements du premier ordre, résultat numérique, tabelle numérique de valeur, propriété optique, utilité, corrections to the phase contrast theory. We can obtain a better approximation to psi n by using more accurate approximations of the two-dimensional integrals, double integral dxq dyq uq times e to the I k dot qp over qp. Such approximations can be obtained from any finite number of terms of the asymptotic series, and then it's got that kind of as related to a series according to an infinite summation, the terms of the 4n times n factorial squared of del and 2 and then of Dicke and this sort of thing, making a notation for this two-dimensional Laplace operator. Two-dimensional Laplace operator. So this is the harmonic theory and the harmonic functions, those being all Laplacians, and whether or not the theory of potentials is just the study of those, and then whether or not, because those are only the partials, that they actually are complete, which they are not. So that's something to get figured out a little bit more. And the Poisson's equation. Scattering of radio waves in the ionosphere. The elastic scattering of X-rays. The exact differential equation to be applied here is a bit more complicated, so the above theory has to be modified. Theory may possibly extend to problems with a complex valued function in which the imaginary part of f corresponds to an absorption. This may be important in order to include the effects of inelastic scattering in an electronic problem. From see also M. von Lau, Röntgen-Strahl interference in Berlin, 1941. Theoretical study of quality of images. Light optics, magnitudes of revolving power and wavelengths, giving account of the effects of aberrations in electron optics. In light optics, the objects to be considered are composed of luminous sources, can be either perfectly incoherent, photography, astronomy, etc., or partially coherent, as in the case of microscopy. We have studied the two extreme cases of perfect incoherence and perfect coherence of phase, for which the basic principles of the formation of the image are very simple. So it's talking about the usual idea of images and virtual images and lenses. And then there's another idea of focus. This is this Fresnel large lens focus, is the idea that go along with gravitational lensing, which is supposedly, explained why relativity worked or something like that. Is that that is an aspect also of lensing, but there's no lens involved as an essential lens. Instead, it's by an occlusion that it goes around. Usually explained quite, at least halfway well. I mean, it's better than, it's about half off what was Newton's was off, the aberration of Mercury's precession. In optics, and also as is discussed here with the idea of like when the halo comes around or the sun's image makes its way through an object, or the ergo spot. The ergo spot is it's often called. Although there's another discoverer who's as well mentioned for it. But ergo didn't have so many things named for him, so it's either easier to name the ergo spot for ergo than this other person who had all these different things named for him. M. Diffuse work. The losses of contrast due to small aberrations. The case of third order aberrations. Rayleigh limit, lambda over 4. Find losses. Find more precise tolerance than the Rayleigh limit. Coma, aberration. Astigmatism, coma, spherical aberration. So this is just an example of getting into helping explain the mise au point sur la focale and showing light's behavior in a diagram. Discussion. Dr. L. Martin, National Bureau of Standards. How far do you think these can be directly translated into electron optics? Marischal says, what we've studied is the two extreme cases of perfect coherence illumination and perfectly incoherent illumination. Glaser said that what is not taken into account is the way that one point diffracts. If considered the case of perfectly incoherent illumination, I'd like to ask Dr. Glaser whether they can't consider the illumination is practically uniform. So, yeah, electrons are not light, though their image sort of behaves like light. So more to that is his own thing. But it's discussed some further in the ideas of like the light theory and about the electron theory. Stress solids and waves by H. Kolsky. So this is with regards to the elastic and the stress waves. Copyright 1963 by Dover Press. Originally published by the Clarendon Press, Oxford in 1953. The theory of the propagation of elastic waves in solids was developed during the last century by Stokes, Poisson, Rayleigh, Kelvin, and others as an extension of the theory of elasticity, the problem of vibrating bodies, and also a help in their studies of transmission of light, considering as vibrations of an elastic ether. Elastic waves of high frequency can be produced and detected easily, and ultrasonics is rapidly becoming a subject of its own. So here it's with regards to the waves and the spiral waves. And so the idea is that there's a complementary aspect of any kind of flow, that there's anomaly, abstractly non-zero flux in the other direction. And so when there's like a wave, it also trails back out. It resounds, and there's resonance, and that resounds. So kind of like Huygens' principle about waves, that waves make waves as they radiate, is that waves make resonances make waves as they resonate. Resonation is usually the idea of the standing wave building up, and otherwise a system with inputs and outputs. That wave and resonance theory, kind of like atomic and molecular chemistry, a lot like, sit up above the idea of the point particle and then particle-wave duality, which is this profound superclassical concept that we were all given in high school, at least. Besides finding it for yourself, having it part of the linear curriculum as presented, that otherwise quantum mechanics could never even be where it is. And it's superclassical. Besides Zeno's superclassical motion already, that particle wave duality is the thing. So this wave resonance duality is just kind of as of building it and cascading, and then the criticality and cascading of those. So it's usually waves is the idea, energy and waves. But it's a tetrad of quantities, and there's wavelets and waves, and there's particles and resonances. So this gets sent to the computator as a series of partial differential equations, is the usual idea, to crunch it and solve it. But that's not complete, and so the nonlinear and the non-standard but super standard is why that's very compelling to have this kind of idea of the theory, because otherwise it would just be quite simple and wouldn't though reflect reality, because reality does all the things. Reality is super classical. Reality is more than merely partial, and these kinds of things. And and whether it's unlinear is another thing, but worlds do turn in reality. The curve obtained by plotting A tau against tau gives the relaxation spectrum of the material, and in general this can be more easily related to the microscopic processes which produce relaxation than the memory function itself. Gross, so there's several Grosses, and some of them are very, very good scientists, discusses the mathematical transformation required to determine the function at when f t minus t is known. It should be noted that in the Maxwell model, when the strain is kept constant, the stress asymptotically approaches zero. When the strain is kept constant, stress asymptotically approaches zero. But they're always in a constant interplay of sorts. This will apply to any number of Maxwell elements joined in parallel. For real solids, it is found that the stress generally tends to a finite value. This can be allowed for by having a second spring. In the case of the Boltzmann equation, this means that if epsilon is kept constant, the integral approaches asymptotically a value a epsilon, which is less than f epsilon. The stress-strain relation for strains, which have been maintained for a long time, then become sigma equals f epsilon minus a epsilon, this being the relation between sigma and epsilon for the auxiliary spring. The Voigt model does not show stress relaxation, since if the strain is fixed, the stress is also fixed. So this gets into relating the Voigt and Maxwell models, and then other ones, like this would be Kolsky's model, or Gross's model. Well, Gross just gave a form for, like, this is an approximation to first order, and these kinds of things. And so these would be Kolsky's models, and Lederman, Lederman, and Gross. So, And then the bibliography of this book is many technical references that are cool and relevant. Landau, Zener, Vert, Whittaker. List some books and review articles on subjects discussed in this monograph, which have appeared since 1953. So, yeah, this Kolsky Stress Waves and Solids is pretty good. Here's a little book by Nietzsche. Ecce Homo. Same. And Ecce reminds me of there's a character from Irish mythology in Finn Ecce's. And so whether he's Roman or what, or Scott, Finn Ecce's is something. But this is about man, and so Friedrich Nietzsche, here he's discussed as one of the anti-Platos, along with Heidegger and Wittgenstein, where Heidegger was an angsty, anxious hen, and Wittgenstein was a hothead, and Nietzsche was a madman. And one thing that Nietzsche was often searching for was his eternal text. And so I found in Quine the other day that, like, here there's this Comenius language, is this eternal text. It's all the truisms. We don't know what they are, but they exist. And so the idea then this eternal text is also related to Quine, who also calls it eternal text. And that it's the thing. It's like, well, some things, if it's free of being modal or temporal, then it's an eternal text. And so let's take a look here at this one. This is one of Nietzsche's works. And I've studied a little bit more thoroughly before, but it's probably been a while. So this was in 1909 to 1911, whereas Nietzsche lived up to 1900, it says. So this was just reprinted from that, from the complete works of Friedrich Nietzsche. Translator's introduction. Ecce Homo is not only a coping stone worthy of the wonderful creations of the ear, but also a fitting conclusion of his whole life, in the form of grand summing up of his character as a man, his purpose as a reformer, and his achievement as a thinker. As if half conscious of his approaching spiritual end, Nietzsche here bids his friends farewell, just in the manner in which, in the twilight of the idols, he declares that everyone should be able to take leave of his circle of relatives and intimates when his time seems to have come. That is to say, while he is still himself, while he still knows what he is about and is able to measure his own life and life in general, speak of both in a manner which is not vouchsafed to the groaning invalid or invalid, to the man lying on his back, decrepit and exhausted, or to the moribund victim of some wasting disease. Nietzsche's spiritual death, like his whole life, was in singular harmony with his doctrine. He died suddenly and proudly, sword in hand. Kind of fell on it, really. War which he and he alone, among all the philosophers of Christendom, had praised so wholeheartedly, at last struck him down in the full vigor of his manhood and left him a victim on the battlefield, the terrible battlefield of thought, which there is no quarter, for which no Geneva Convention has yet been established or even thought of. I don't know about that. We have one where things are at least fair. So Nietzsche, when you first learn about him, and the idea that he has like will to power and this kind of stuff, and there are other things to consider with regards to philosophies of what the will is toward. So it's not always towards power. And then the idea is like, well, God is dead, so we must, make ourselves mighty. People definitely have used that as an abuse of what would otherwise be reading of it. Because even this translator's preface doesn't really necessarily agree with what I took away from reading Nietzsche at all. And there's Thus Spake Zarathustra and stuff like that. So reading Nustra is an exercise in frustration and pity. But naively, when you first start reading it, it's elevating. And so it's one of those things you get figured out. As I, Nietzsche, am speaking here of the recreations of my life, I feel I must express a word or two of gratitude for that which has most refreshed me by far the most heartily and most profoundly. This, without slightest doubt, with his friendship with Wagner. So that's kind of a thing. So yeah, he basically says that he would never be part of the people who most took this word and kind of blew it up to say something that it doesn't. So yeah, Nietzsche was an anti-Plato, but then he's also kind of a Platonist again. I'm not. He's talking about Schopenhauer and optimism and pessimism. Bad smells. I tend not to rely on my sense of smell at all. It's kind of neglected. It's present, but it's mostly just a detector, not a sensory device. It is thus that he recovered from being a god. And Nietzsche says, I guess, he had made everything too beautiful. So in this sense, maybe Nietzsche would be able to find the eternal basic text again, and then also as well recount. The idea of the Nakbat stuff. He would be able to go over it again and bring it back again. The hard sayings of Jesus, F.F. Bruce. I'm not quite so sure why this is here, and so and it's not going to be really included, but it's in the box. You cannot serve God and mammon. Matthew 6:24, Luke 16:13. Says the hard sayings. Well, gentle readers, about 2/3 of the way through this box here. See if there's anything really to sample of it. Stellar physics. So here's the stellar physics, and the other volume here is called stellar pulsation. And this is about ionized plasmas, so this would also be about fusion or stars and this kind of stuff. Have a great day. The hour is upon us. Tempus fugit. Good day, gentle readers, fellow earthlings.